Hey guys, welcome to video 83. Today we're going to be taking a look at BJTs, MOSFETs, and Triodes and trying to get a handle on why they sound different from one another in amplifier applications, and in particular Class A amplifiers. Now we're going to take an approach almost from a first principles level here, and I don't mean quantum mechanics or anything that fundamental, but it's going to be pretty mathematical, but still I think it's pretty interesting stuff, so hopefully you'll stick around. Now, something we need to keep in mind is that we're looking at these things from the perspective of guitar amplifier design, not hi-fi. And in guitar amp designs, most of the time we're going to be using little or no negative feedback. And this means that the device nonlinearities are going to be very pronounced. Now, normally when we analyze an amplifier, what we'll do is develop a small signal model for the device, and we treat it as a linear device over its entire operating range until we hit clipping. And treating them as linear devices simplifies the math and the analysis, and usually it's good enough for our purposes. Now, we know they aren't linear over their entire operating range, and if we start over here with the BJT, hopefully you'll remember that the collector current is an exponential function of VBE. And down here I have a typical transconductance curve for an NPN transistor. The MOSFET, remember, is a square law device. Its drain current is proportional to VGS squared, and the triode is what's called a 3/2 law device. The plate current is proportional to the grid to cathode voltage raised to the 3/2 power. Now, if we just do a real quick comparison of these three equations, the exponential that describes the BJT is going to be the most nonlinear of the three. But between the MOSFET and the triode, it appears that because the triode is raised to a higher power than the MOSFET, that it's going to be more nonlinear. But that's not necessarily the case, and we'll find out why soon enough. But what I want to do next is go on over and take a closer look at the BJT and its nonlinearities. So if we go on over to the next slide, we're going to do a quick review of what we covered back in video 53. The circuit we're working with over here is just the typical voltage divider biased Class A amplifier, and I hand selected a transistor to work specifically for this circuit in an experiment, and it's got the parameters shown over here, and this is a graph of its transconductance curve. Now let's just review the parameters in Shockley's equation for the transistor for a second. I sub S is the saturation or leakage current for the base emitter junction diode. It's typically a really small current, in this case about 0.1 nanoamps. V sub T is the thermal equivalent voltage for the diode, and at typical operating temperatures it's about 26 millivolts. And finally, eta is the emission coefficient, and for general purpose transistors like the 2N3904, it's usually around 1.5. Now, of course, most of the time when we're working with a circuit like this, we're not going to be using Shockley's equation. We're just going to make a bunch of approximations, and we'll use parameters like I have shown over here to get a location of our Q point, and we assume it's a linear amplifier and just go from there. But in this particular case, we're really interested in the nonlinearities of this equation, and so what we've got here is a graph of the transconductance curve for this transistor, and we've located the Q point at ICQ is 1.75 milliamps, VBEQ is 0.65 volts, and we're applying a sine wave to the input that causes the Q point to move back and forth on the VBE axis by plus or minus 0.035 volts. And it gives us this resulting change in collector current, and the waveform associated with it is shown here, and of course we see there's a lot of nonlinearity going on here. Now, what we did back in video 53 was derived an equation that describes this curve, and that's what we're going to take a look at next. Now, we're going to walk through the derivation a little bit quickly here. If you want to see a more nuanced presentation, go back to video 53. But we're going to start here with Shockley's equation for the collector current. The first thing we'll do is drop this -1, and we're justified in doing that because the exponential over here is usually a few million or so, making this pretty insignificant. And that gives us this simplified version of Shockley's equation here for equation number 2. Now, VBE is the total base to emitter voltage. That's VBEQ plus Vin, and substituting that into Shockley's equation allows us to split this into two parts. We've got the first factor here, which is ICQ, and the second factor, which is the variation in collector current due to Vin. Now, we write that down here, and we can take the exponential and expand it into what's called an infinite power series. And in this case, it's really a Taylor series, but we get this really ugly looking expression down here that can go on forever, but we're truncating it here at the third power. The next thing we do is multiply ICQ through the factor on the right in parentheses, and that gives us equation 4. Now, if we're dealing with a linear approximation of the amplifier, we just use these first two terms and we ignore all the higher power terms over here, Vn squared, Vn to the third, and so on. We just assume that they're negligible. But again, in this case, because we're trying to figure out exactly what's going on in the output, we're going to keep these terms. And if we factor out ICQ over A to VT from each of the terms, we get equation 5. Now, this is even uglier and scarier looking than equation 4, but it's kind of convenient because it did isolate this ICQ over A to VT factor. And the reason why it's nice to have this factor separated out is because ICQ over A to VT is the transconductance of our transistor. So we can rewrite this equation in a little nicer form down here as equation 6. And if we look at this equation term by term, here's what we've got. The first term, ICQ, that's DC. It'll get blocked by the coupling capacitor, so we're not going to worry about it. The second term here, GM times Vn, is the linear gain term. That's going to give us our fundamental is just a constant times Vn. The quadratic term will give us our second harmonic in the output, and notice it's scaled by GM divided by 2A to VT. So generally it's going to be lower in amplitude than the fundamental. The third term here, well, actually the fourth term, but it's the third harmonic, is given by the cubic, and its coefficient should be even smaller yet. And this is why we normally disregard these terms out here past the linear term. Okay, so here we're dealing with current, but we'd rather be looking at the output voltage. So if we multiply IC times negative R prime C, we get the output voltage, and that's what we have in this next equation down here. And again, rather than dealing with transconductance, we can express this in terms of voltage gain. Because AV equals negative GM times R prime C, we can just make that substitution. And finally, we get the equation V out equals AV times V in, as we've always seen in the past, plus the quadratic and then the cubic and so on. So now we have a really useful equation to work with. Now let's go on over to the next page and we'll look at the circuit that I actually built back in video 53, and let's examine what happens when we apply a sine wave. The actual experimental circuit is over here. We adjust it for a collector current of 1.75 milliamps and apply a sinusoidal input of 35 millivolts peak. The frequency used is 1 kilohertz. That's just the typical standard test frequency. And here's our output voltage equation. When we substitute in this sine function, we get this messy looking thing here, and in order to make sense of this, we have to expand the sine squared and sine cubed factors using these trigonometric identities. And if we take a second to look at these trigonometric identities, we see that the sine squared is going to result in a DC component and an inverted cosine waveform at twice the original frequency. The sine cubed factor is going to give us a sinusoidal component at the original frequency and an inverted sinusoidal component at 3 times the original frequency. So we've got a component at the fundamental, that's this original frequency, the second harmonic, and the third harmonic, plus a DC term thrown in there as well. Now if we substitute in our values for Vin and a voltage gain of -135, this is the output that we get. The first term, our fundamental, is just the normal output that we'd expect if this was a linear amplifier, and we've got a negative sign because it's inverting. The second term is the DC offset we get from the expansion of the sine squared. Over here, the next component is, again, from the expansion of sine squared. It's our second harmonic with the same amplitude as the DC component. Now the cubic contributes a sinusoidal component that's got the same phase as the fundamental, so these two components are additive. And finally, the third harmonic comes out the smallest with an amplitude of 0.16 volts peak. Now, since these two terms have the same frequency and phase, we can just add them together and bring it down. And if I just neglect the DC component to keep things as simple as possible, here's what we get out. -5.21 sine omega t, so that's our fundamental, plus 1.06 cosine 2 omega t, the second harmonic, and 0.16 sine 3 omega t, the third harmonic. Now, we can estimate the total harmonic distortion of the amplifier using the usual THD equation we've looked at previously, and in this case, we get a total harmonic distortion of about 20.5%, which is pretty high, but that's not unusual for this sort of amplifier. We have no negative feedback at all, so it's going to be pretty nonlinear, as evidenced by this distortion. Now, the output voltage equation is very beautiful and informative, but it's probably kind of hard for most people to wrap their heads around this. So what I'm going to do next is show you the Desmos plot of this equation using the values we've got here, and this is what I came up with, and it looks pretty much like you would expect it to for this kind of amplifier that's driven pretty hard and showing a decent amount of distortion. And I also pasted in the original oscilloscope capture from when I built the circuit, and we can see that the output waveform shown here in yellow really matches up pretty closely with what we predicted in the analysis, and that's always nice to see. We've got a peak amplitude of the output of about 3.9 volts over here. You can see here's 4 volts, so we're right about 3.9, and we've got a negative maximum of -6 volts roughly, and we can see over here we're pretty darn close to -6. So all the pain we endured in that analysis actually seems to be worth the effort, and I mean, what more can you ask for? You build the circuit, it looks exactly like what the predictions are. We're going to take a look at the MOSFET next, but before we do that, I just want to mention one thing about our derivation here. The method we used to figure out how the transistor was going to behave was to expand its exponential equation using a Taylor series expansion. And technically, there are limits to where we can apply this kind of expansion. And in particular, in this case, it only applies really accurately when we have a small signal. That is, when Vin is small compared to eta times Vt, and that works out to be about 39 or 40 millivolts peak. So we're really close to the limit here. We've got 35 millivolts peak for our input, assuming everything here is perfect. So if we were to make V in much larger, this approximation would become less accurate. But considering that we're very close to the limit here and our results were really good, I'm happy with what we've got, and this is a pretty good approximation of how the transistor is behaving. Now let's go on over and take a look at the MOSFET. This analysis is going to go a lot faster than for the BJT because we don't have to do anything fancy like Taylor series expansions. So we'll start with our normal drain current equation and substitute in VGS equals VGSQ plus the input signal, which gives us this little bit messier looking equation here. We also can substitute in Vin as a sine function, expand that out, and using FOIL and a trigonometric identity, we come up with this drain current equation down here. We've got a term for IDQ, the transconductance, the fundamental, a DC term from the quadratic, and we get our second harmonic term on the output as well. And if we simplify this a bit by just substituting these identities, we end up with this drain current equation. And ignoring the DC terms, and we get, finally, crunching through all the numbers and expressing it in terms of voltage gain rather than transconductance, we get our output voltage, which has a linear term, the fundamental, and a second harmonic term due to the quadratic. And ideally, there are no higher power terms, no third, fourth, or so on, until we hit clipping, but that's not really true because there are some other effects that come into play. But if we ignore them, ideally the output should consist only of the fundamental and a second harmonic. Well, that was a lot faster than the BJT analysis. Hopefully it wasn't too fast and it made sense. We've seen most of these things applied previously, so I figure, it's probably okay. But what we're going to do next is go on over and take a look at the results we got from video 52. And here's the circuit that we analyzed and we constructed it. Don't get distracted by all this stuff over here. This is just the parameters for the quadratic formula used to determine the Q point. We've got our AC load line, DC load line compliance equations, and a list of theoretical and measured values. What we're concerned with here is the small signal analysis. So up here is our AC equivalent circuit. We've got a voltage gain of -22 and our input signal is 0.2 sin omega t volts. Now this isn't really what I'd consider a small signal. It's driving the amplifier pretty hard, but it's not producing clipping, and we don't have to worry about exceeding the limits of a power series expansion approximation, so this should be okay. Now if we plug these values into our Vout equation, we end up with Vout equals -4.4 sin omega t, our fundamental, plus 0.53 cosine 2 omega t, the second harmonic, and the total harmonic distortion here is about 12%. And if we compare this with the BJT we looked at previously, it was over 20% at roughly equivalent output voltage swing levels. So more or less comparing apples to apples, we see that the MOSFET is a lower distortion device relative to the BJT, at least in terms of this ideal analysis. And again, because it's kind of hard to visualize an equation like this, I did a plot of the equation using Desmos. I don't know what this -8 is here, little artifact, but in any case, this is the output we get, and we do see the kind of squashing and stretching on the positive and negative going outputs, but it's not as bad as it was, at least plotting this equation, as it was for the BJT. We're reaching almost 4 volts on our positive peak and about -5 volts at the minimum. And I also pasted in the oscilloscope trace that we got for the actual circuit, and you can see the distortion is a little bit higher in the real circuit than it is for our theoretical analysis here. Our output is reaching a peak of 4.4 volts over here versus a little less than 4 here, and our negative minimum is minus 6.4 as opposed to about minus 5. So the real MOSFET is exhibiting a bit more distortion than our theoretical analysis, and that's because there are higher order effects coming into play here that we're not accounting for in this output, but it's still reasonably close, and the distortion is not as bad as it was for the BJT. And finally, we're ready for the part I'm sure everyone's been waiting for, and that is the triode. So just like we did with the BJT and the MOSFET, we're going to start with our plate current equation where VGK is the total grid to cathode voltage VGKQ plus Vin. And this time, because we've got a 3/2 power law equation, we're going to use a binomial expansion to model the behavior of the triode. Here's our expansion, and again, this can continue out for infinitely many terms, but we're going to stop it here at the cubic. And we have to define a couple of other parameters for use with this thing. We've got V sub q, which is VGK at the q point plus VPKQ divided by mu, and another parameter x, which is Vin divided by V sub q. This is, kind of a complicated thing to derive, and I'm not going to bother going through it, but this is the x that we'd use in our binomial expansion here. So when we substitute this stuff back into the expansion, we end up with equation 6, and multiplying through by this first factor, we get equation 7, and neither of these are very nice looking equations. There's a lot of stuff going on here, and it's more than I really want to go into on this video, so you'll just have to take my word for it that this is what we get, and you can verify this yourself algebraically if you're really feeling energetic. But coming down here, if we express K in terms of the transconductance, we get this equation. And finally, if we substitute this one into equation 7, we get equation 9, which is starting to look a little bit nicer. Now, as usual, the IPQ term is blocked, and the output voltage is given by negative IP times R prime P. We've seen this many times before. That's from the AC equivalent model. And grinding through all of this stuff, we finally get an output voltage equation in terms of transconductance, and again, we normally prefer to work with voltage gain, so AV is negative GM times R prime P. Making that substitution, we get a nice equation, at least relatively nice for V out here in equation 11. So we have a linear gain term here, plus the quadratic with this coefficient and the cubic term with this coefficient. And notice that the coefficients are getting small pretty quickly. We've gone from 1 over 4 to 1 over 24, and the remaining coefficients out here diminish even more quickly. And just like the case of the Taylor series expansion with the BJT, there are input voltage limits we have to watch out for to keep this approximation valid. For a small signal, we're going to define that as Vin being much less than V sub q, or alternatively, the ratio Vin over Vq should be much less than 1. The smaller it is compared to 1, the more accurate this approximation will be. All right, now let's go on over to the next page and apply this information. Over here on the right, we've got the circuit we used back in video 62. We set it up for a Q point of 750 microamps, VPKQ of 125 volts, using a 12AX7, and we get a voltage gain of negative 48. So if we plug the numbers into our equations we just derived on the previous page, We get a VQ value of about 0.15 volts, and setting V in to 0.1 sine omega t, we've got a 0.1 volt amplitude. That gives us a ratio here of 0.7 for Vin over VQ. And remember, we want this to be much less than 1 for really accurate results, but this is okay. It's not great, but we can still use our binomial expansion, which is shown here in equation 2. So if we substitute everything in and go through all of our trigonometric substitutions, we end up with V out equals this big mess with some DC terms we're going to ignore. Come down here. We finally get V out equals negative 4.8 sine omega t. That's our fundamental. The second harmonic is pretty small with an amplitude of 0.086 volts peak. And the third harmonic is really pretty small. It's only about 2.9 millivolts peak. So the total harmonic distortion for this case is only 1.8%. That's reasonably low for a guitar amplifier. We're going to take a look at the graph of this equation in a minute, but first I want to put things into a little better context. Back in video 62, we showed that this amplifier can produce an output voltage of greater than 100 volts peak to peak before clipping occurs, and we're only using a very small portion of that output voltage swing available here, so it makes sense we've got a pretty low distortion. Now, if we look back at the BJT and MOSFETs we just analyzed, we were probably using about 90% or more of the available output voltage swing for those circuits. So it makes sense that they'd have pretty high distortion. Now, we can't really make a good comparison with what we've got here right now, but we'll get to that in a minute. So let's go over and take a look at the graph of our output equation here. And you can see that really there's not any distortion visible here, and that makes sense. It's only 1.8% THD, so this looks pretty good. Now let's go over and take a look at some oscilloscope traces we got from the experimental circuit. In this case, we've got an input voltage of roughly 1 volt peak to peak, and we're getting about 55 volts peak to peak on the output. So our gain is around negative 50. And you can see that the output voltage is again showing very little distortion here. And this is an even larger input than we did in our analysis. We're reaching a positive peak output of about 26.7 volts and a negative output peak of about minus 28.6 volts. So there's not that much asymmetry present. And you can use that as a general judge of the amount of distortion. The more asymmetrical we are on these two peaks, the more distortion we have. Now let's go on over and take a look at what happens when we drive the amplifier pretty hard. Here we're using a 2 volt input, 2 volt peak to peak input signal swing, and we're getting about 94 volts peak to peak out. We can see there is the classic squashing and stretching starting to show on the output waveform, but it's still not that bad. We have a positive peak of 42.8 volts. Our negative peak is minus 51.4 volts. So there's more asymmetry, but again, it's not that bad. So at this point, let's just kind of do a comparison of the three devices. Okay, here we've got the three equations we derived today, and underneath each one is a scope capture that shows the amplifier producing about the same proportion of the usable output voltage for each amplifier. Starting over here with the BJT, the output is about 9.9 volts peak to peak, and we see the squashing and stretching of the positive and negative peaks that we come to expect from these Class A amplifiers that don't have any feedback. The distortion here is pretty extreme. It worked out to be a little over 20%, and it's mainly because we have this really strong second harmonic. Coming over to the MOSFET, we've got an output of about 10.9 volts peak to peak. And again, we see the asymmetry with the squashing and stretching of positive and negative peaks. And it's very similar to what we got for the BJT. Not quite as bad. The distortion for this one theoretically was about 12%. In practice, for this waveform, it's probably more like 15% or so, because we're going to have some third order effects and higher out here, but they're just not modeled in this equation. But we do have a very strong second harmonic, and that's going to manifest itself in this kind of distortion. Now, we come over to the triode, and this is interesting. We've got an output of about 94 volts peak to peak, roughly the same percentage of its maximum available voltage swing, but the distortion is noticeably lower here, and that's because the coefficients of our quadratic, cubic, and higher terms drop off really fast compared to the BJT and MOSFET. The third harmonic here isn't even really that significant, but because it's got a negative sign, it does tend to compensate a bit for the second harmonic, and we see that we get a pretty distortion output here. It worked out to be about 1.5% or so for the ideal case. In practice here, with such a large output, it's probably closer to 5% in reality, but this is one of the reasons why triodes are preferred in guitar amplifier applications over MOSFETs or BJTs. They just have a totally different response equation, and it manifests itself in a nicer sounding distortion. Now, in an ideal world, I'd go on and push these amplifiers to clipping and do some comparisons, but this video is already plenty long, so we're going to wrap it up here in a second. I'm just going to go on over to the next page, and we're going to do a little graphical comparison of the distortion characteristics we saw here today. All right, now in order to have the second harmonics show up on the graph, I had to use a logarithmic scale here on the vertical axis, and I normalized the distortion relative to our output waveforms, and we can see that the BJT has really high second harmonic distortion and pretty strong third harmonic distortion as well. The MOSFET ideally has no third order or third harmonic distortion, but we know there's going to be some there. But the thing to notice here is that it does have relatively lower second harmonic distortion compared to a BJT, and that's why it's a more linear device. And then finally, we've got the triode, and it's got the lowest harmonic distortion levels, all things considered. And even though it does have some third harmonic distortion coming up here, the thing we have to keep in mind is the sign of this component is the opposite of the second harmonic. So overall, it kind of makes the distortion a little bit nicer. All right, and that's it for today's video. Hopefully you got something out of it. Maybe it was interesting, I hope. But anyway, that's it for today, and I'll see you guys next time around.